All right, so today we will continue our discussion of NP-Completeness. So the main concepts today are going to be verification or verifiability and the notion of a reduction and complexity classes. So these are going to be the main concepts. Okay, so let's first review the main concepts from previous lecture. So the first concept was an informal definition of NP-completeness. So an NP-complete problem is a problem for which there is no polynomial time algorithm that can compute the exact solution to every instance of the problem. So if there is a polynomial time solution that can compute the approximate solution to some or even all the instances, that's not an NP-complete problem. So, and if you have a non-polynomial time solution that can compute an exact solution to every instance, that can still be an NP-complete problem, because NP-complete problems are usually problems that are looking for a combination or a permutation. So if it's looking for a combination, exhausting all possible combinations can be done in exponential time. And if it's looking for a permutation or an order, exhausting all possible orders can be done in factorial time. So it's, you can always find that brute force solution that runs in exponential or factorial time. And in practice, there are many NP-complete problems that are handled in practice using either approximation algorithms or even greedy algorithms or greedy heuristics. So greedy heuristics. In this context, a heuristic is an algorithm that is not guaranteed to give the optimal solution. So if an algorithm is not guaranteed to give an optimal solution, we call it a heuristic. And that's how we normally handle NP-complete problems in practice. Okay? So these solutions exist, but from a theoretical point of view, we would like to have a solution, a polynomial time solution that is guaranteed to solve every instance of the problem exactly. And for these NP-complete problems, such an algorithm does not currently exist. And so nobody has come up with such an algorithm, but nobody has proven that such an algorithm does not exist either. So we don't know if there is such an algorithm or not. If a polynomial time algorithm to an NP-complete problem exists or not. This is an open question, but most people believe that such an algorithm does not exist. But no one has proven that. Okay, so in today's lecture, we will focus on first on the concept of verification. So verification is related to the concepts of decision versus optimization problem. So last time we had an optimization problem, an example of an optimization problem, and an example of a decision problem. What's a decision problem?
Yes.
Yeah, exactly. So it's a problem for which the solution is just a yes-no. So it's just a yes-no. While an optimization problem is a problem for which the solution is finding, is maximizing or minimizing a certain cost function. Okay? And the example that we presented for an optimization problem was the TSP. That was the example. The example of a decision problem was subset sum. Now, in last lecture, one thing that we did in last lecture was recasting the traveling salesman problem as a decision problem. So how did we recast the traveling salesman problem into a decision problem? How did we do that? How did we recast the traveling salesman problem as a decision problem? So the idea was to set a certain target, to say, given a graph, a complete, weighted, undirected graph, and given a target cost t, determine if there is a TSP tour with cost less than or equal to t. So given a graph with weighted, undirected, and a target cost t, determine if there is a TSP tour of cost less than or equal to t. Okay? Now we can talk about verification of or verifiability of a problem. Now a problem, we say that a problem is verifiable. A problem is verifiable in polynomial time if you can come up with a polynomial time algorithm that can verify the correctness of a proposed solution. So you are given a problem and someone gives you a proposed solution, and your job is to determine if the proposed solution is correct or incorrect. The question is, can you do that in polynomial time or not? So let's see if we can do that for the problems that we have studied last time. So for the subset sum, so given a set S and a target T, so someone gives you a proposed solution, let's call it S prime. Someone gives you a subset. So let's put just some numbers. If S equals 2, 3, 4, and T equals, so this is an example. S is 2, 3, 4, and T is 7. Someone says, OK, this is a proposed solution for you. S prime equals 3 and 4. And your job is to determine whether the proposed solution is correct or incorrect. Now, given an instance of the problem and a proposed solution, can you verify in polynomial time if the proposed solution is a correct solution or not? How can you verify this? What do you need to do?
We can add all the elements and check if it is equal to t, and then we can, if it is correct, then we can check if they exist in the original set.
Yeah, exactly. So you have to check two things. You have to check, first you have to check if these elements exist in the set or not. Right? So you have to search for 3 in the set, and you have to search for 4 in the set. So you have two search problems. Even if you do, if the set is not sorted in any way, and you do linear search for each one, so this is, if this is in the worst case n, and this is n, so in the worst case, this is n squared, right? So you can do in n squared, you can search for these given elements to see if they are in the set or not. Then you compute the sum and see if the sum is equal to the target or not. If both tests pass, then this is a correct solution. So here you can easily determine in polynomial time if a proposed solution is correct or not. So this is what we call verifiability. So the subset sum is verifiable in polynomial time. is verifiable in polynomial time. Okay, so now let's switch to the traveling salesman problem in its optimization form. So given a graph, so someone gives you a proposed solution, and a proposed solution is for the traveling salesman problem. What will that proposed solution look like? What's the solution to the traveling salesman problem?
A tree.
It's a cycle, right? So they have to give you a sequence of vertices. What's a cycle? A sequence of vertices. So it's sequence of vertices. Can you verify that this is an optimal solution? Because a correct solution for the TSP optimization, the optimization version of TSP, is an optimal solution. So if someone tells you, okay, I have this solution for you, E, A, B, C, D, A. Suppose that this is our instance, the one that we did last time. If someone gives you this instance and someone gives you this solution, can you verify that this solution is indeed optimal?
You have to get the optimal solution from the TSP optimal and then check this proposed solution with that, and that would be a lot of.
Well, and we don't know how to find the optimal solution, right? Yeah. So there is no way to verify that a given solution. There is no way to generally verify that a given solution is optimal unless you solve the optimization problem itself. So, okay, someone gives you a solution. You have to first verify that it satisfies all the constraints of the problem. So in this case, you want to verify that all of these vertices belong to the graph. So you want to make sure that someone doesn't give you a solution like this, A, B, E, C, D, A. So this is an invalid solution because it has a vertex that does not belong to the graph. Or someone gives you, A, B, C, B, C, B, some path that is not a simple path. So this is not a TSP tool because they are repeating B multiple times. So this is invalid. So I have to check all of this. This is easy to verify. But what is not easy to verify is optimality. To verify that it's optimal. And I can calculate the cost of this. I can just sum the edge weights, and this will give me, 4 plus 4 is 8. So this is a correct solution. It satisfies all the constraints. It's indeed a cycle, and all the vertices exist in the graph, and I'm not repeating any vertices, and the cost is 8. But so what? Is 8 optimal or not? Now, generally speaking, in order to answer this question in general, you have to solve the optimization problem, which is something that we don't know how to do in polynomial time. But in some cases, if someone gives you a solution and you calculate the cost, in some cases you will be able to tell that it's optimal. When?
Can you show a counterexample?
I'm sorry?
Can you show a counterexample? Can you show?
Oh, a counterexample?
Can you find a better solution?
Find a better, yeah, if you can find a better solution, but in general you don't know how to do that, right? You don't know how to find a better solution. You may or may not find a better solution. But under what conditions will you be able to prove that a given solution is optimal? Yeah.
If you were given a target, like in
We haven't discussed this yet. We haven't moved to the decision version of the problem yet. Okay, so we're still talking about the optimization version of the problem. So under what condition you may be able to say that, yes, I know that 8 is indeed optimal, given what we have discussed last time? Well, if the cost of this is equal to a lower bound, if you can calculate a lower bound, remember the lower bounds that we have calculated last time, they can be calculated in polynomial time. So usually you can calculate lower bounds in polynomial time. And if the cost of this proposed solution happens to be equal to the lower bound, then it's provably optimal. Then you know that it's optimal because it's equal to the lower bound, right? But this will not work in general. You know, this is not guaranteed to work in all cases. So in some cases, if your lower bound is tight enough, then you may be able to catch, you know, some of these cases and prove them optimal. But this is not general enough. This will not work in all cases. Okay, so this is the verifiability problem. So TSP optimal is not verifiable in polynomial time. TSP optimization is not verifiable in polynomial time. Now, what about TSP decision? Now, if we switch to TSP decision, the decision version of the problem, so you are given a graph and you are given a target. If someone gives you a proposed solution, which is a sequence of vertices, can you verify that it is correct? It is correct. Now see, the definition of correctness here is different. The definition of correct here is it's an optimal solution. Now, what's the definition of correct in the context of TSP decision? What do we mean by correct for TSP decision?
If it can be a solution or not. That means if it is covering all the vertices.
Okay.
The vertices are not repeated.
Not repeated.
Okay, so that's all of that is a legal solution, but that does not necessarily mean that it's correct. What else do we have to check? Yeah.
If their path is equal to the target?
Yeah, exactly. If the cost is equal to the target. So correct here means it's legal. Legal, it's indeed a simple cycle that belongs to the given graph and meets the target.
Or is less than the target?
Well, the target is normally less than or equal or greater than or equal. So if it's legal, legal here means you verify that all the vertices exist in the graph, which is something that you can do in polynomial time. You just search for these vertices. You can verify that no vertex is repeated, and then you just sum the edge weights, and if they are less than or equal to the target, then that's a correct solution. So is this something that you can do in polynomial time?
Yes.
Yes, you can. So TSP decision is verifiable in polynomial time. So this is a fundamental difference between the optimization version of the problem and the decision version of the problem. And in fact, this will apply to all the optimization problems that we will be studying. So usually the optimization version of the problem is not verifiable in polynomial time because you can't verify optimality. In order to verify optimality, you will have to find the optimal solution. While verifying that a given solution meets a certain target is something that you can do in polynomial time. Okay, so you just sum the edge weights, and that's theta e, and then compare that with the target. And that you do that after checking that all the vertices exist in the graph and verifying that you are not repeating any vertices. Okay? And of course, you know that there is an edge. An edge exists between any given pair of vertices because of what? How do we know that for the traveling salesman problem that there is always an edge between any given pair of vertices?
It's complete graph.
Yeah, because the input is guaranteed to be complete for the traveling salesman problem. The input is guaranteed to be complete. Okay, so now this is the concept. Now in the theory of NP-completeness, there is a difference between problems that can be verified in polynomial time and problems that cannot be verified in polynomial time. So this leads to the concept of complexity classes.